Okay, so now I wanted to say a little bit more about moment of inertia. Remember, that was our rotational mass, and we actually defined it as the sum over all the m sub I r sub I squares. Again, in Math 1B, I think you'll probably do a little bit of this, but you'll use integration, but everything here will be discrete right here. So here I said, suppose we have some points on a coordinate system. You have a point M, mass M at the point 2, 3. You have a 3M at the point minus 3, 1. And you have a 6M at the point at the x, y, 0, minus 4 right here. And I ask, what is the moment of inertia? Now these points are fixed on that coordinate system. What is the moment of inertia about the x-axis? That is, what if I came over here and twisted this going around like this? What would be the moment of inertia about the x-axis? Well, you notice this one right here, just going around like this, the radius is only 1 right here. It's only going around like this. This one, the radius is 3 right here. You notice the radius is just the y value. So I could have written this as just the sum of all the m sub I, y sub I squared. So on this one, we would say it's m times the y value squared, 3 squared, plus 3m times the y value squared, plus 6m times the y value squared. And so that just gives me 9m plus 3m plus 16 times 6 is 96m. Adding them up, that's 108m. So again, the units are going to be kilogram meter squared, but my meter squared is in with the numbers right there. Okay. Now suppose we wanted to spin it about the y-axis. We want to go around this way right here. Well, you notice this, the radius of this one is just the x value. It's just 2. This one has a radius of 3 right here. The minus doesn't matter because you're squaring it. So I about the y-axis is just the sum of m sub I, x sub I squared. And so over here, this one would be m times 2 squared. This would be 3m times minus 3 squared. This would be 6m times 0 squared, which is 4m. That's 27m, 31m. You notice this one would be at least 3 times harder to spin this way than it would be to spin this way right here. And then we could have said, what if we want to rotate it about this axis, the z-axis right here? Well, now the radius is that distance, or the radius squared is x squared plus y squared. So I can replace it with just mx squared plus y squared. But if I just distribute this through, this is just I about the x and I about the y. So I about the z, I can just add these two up right here, and that's what, 139. We could call that the perpendicular, because these are all perpendicular to each other, x, y, and z. I about z is equal to I about x plus I about y. Now this isn't always true. This is only good for flat objects in the xy plane right here. So anytime you have an xy plane, so if we have something like a disk right here, a disk, I about this axis plus I about that axis should be I about this axis right here. Well, we know what I is for a disk. It's 1/2 mr squared. And if these are both the same, then each one of these must be 1/4 of an mr squared. This is 1/4 of an mr squared. This is 1/4 of an mr squared. And that's 1/2 right there. Okay, we could also go back and we could calculate where the center of mass of this is. We'll just do that again. We've done that already. It's the sum of x sub I, m sub I over the sum of the m sub i's. Don't get these two equations mixed up right here. So here, this would be 2m times his x value is 1 plus 3m times his x value minus 3, there give you minus 9, and then that one, the x value is 0, divided by the sum of the masses, m and 3m and 6m is 10m right here. The m's drop out and it's minus 7/10. We could have gotten the y-axis, the y center of mass right here, is just put in the y there. So over here it'd be 3 times m. This one would be 3m times 1. This one would be 6m times minus 4, which is minus 24 over 10. Adding these up, it's minus 18 tenths. The m's drop out, and it's minus 9 fifths. So the center of mass is minus 7 tenths, minus 9 fifths, which is about right there. It should look like it's near the center. It's not the geometric center because you have a lot more mass over here on these two right here. Okay, so we have a way of getting the center mass and the moment of inertia for points right here. There is something called a parallel axis theorem right here. Parallel axis theorem says if this is, say, a disk, and if I know what the I is about this axis, then I know what it is about every axis that's parallel to it right here. It says I about any axis is I about the center of mass of the object plus m times d squared, where d is the distance between these 2 points right here. So if I wanted to say I have a disk and I don't want to rotate it about this point, I want to rotate it about the edge. So it's going like this right here. Then I about this point would equal I about that point, which is 1/2 mr squared, plus the mass of the disk, which is m times the distance from here to here squared, which would just be r squared. Combine these two together, that would give you 3/2 mr squared. So that's what the I is about this axis. This is much more important because this is always true right here. So if I wanted to find out what the I was about this axis right here, I know what it is about that point. That's my point P right there. And that we said was 139 m. So I know what it is about this axis. So I know what that would be 139 m. And that would be the mass of everything, which is 10 m. And that d would be the distance from here to here squared. And I could plug that in. I could calculate that distance. And so I could get the I about the center of mass. It'd be the I about this axis right here. So this is true even for not for flat objects, for three-dimensional ones right here. Okay, so now let's use this thing right here. Suppose we have 3 sticks form an equilateral triangle. Here's just an equilateral triangle. They all have the same length A. They're all 60 degrees right here. The total mass of the whole triangle is m. That means each piece is m over 3 right here. Find the I up through its geometric center right here, perpendicular. So we're going to rotate this about this axis right here. Now I think you have one in the homework which is a square. I'm just doing it for a triangle. So what do? We look at just one stick. There's the stick right there. I'm just going to look at that first. We want to find the I. We know what the I is about the center of mass of a stick. It's 1/12 times the mass of the stick, which is m over 3, times the length squared, which is a squared. So this, for just this is 1/36 ma squared. But I don't want to rotate it about this axis. I want to rotate it about that axis. I want it to go around like this, not like this. So I need to find out what the I is about that point right there. Well, we can use our parallel axis theorem. I about that axis is I about the center of mass, which we said was 1/36 ma squared, plus the mass of this, which is m over 3, times the distance from here to here squared. Well, what is that distance? Well, we know if I make a little triangle here, this cuts this in half, so it's only 30 degrees out to here. And we know that distance is a over 2, that's half of it. And we want to calculate d, so we'll just use the tangent. The tangent of 30 is d divided by a over 2. Throw the a over 2 back on this side, and we know the tangent of 30 is 1 over the square root of 3. So that distance here, the distance from here to here, is a over 2 square root of 3. So if I square that and plug that over here, 2 squared to 3 squared is 12. So that was a squared over 12. So there's the I about the P when I add these two together right there. Okay, but that's only for this stick about that point. Well, this stick about that point is the same, just by symmetry. This stick about that point is the same. So I can just triple it right here. Triple of 1/18 ma squared. Well, that's just 1/6 ma squared. So that's what it would be. You're going to be doing this similar to this for a little square instead of a triangle. Okay, now here I have a hoop. It's a hoop and a disc right here, and I'm going to weld these two together. And this one is 3m, the disc, and this one is m, but we'll have the same radius right here. And I want to know what is the moment of inertia about that point right there. We'll see later that if you know the moment of inertia about that point, and you know where the center of mass is, you can find the period of oscillation very easily from those two right here. So, but we're just going to find the moment of inertia about that pivot point right there. Okay, actually we can do actually I did both. Y of the center of mass. It looks like I did that one first. To get y of the center of mass, here's my coordinate system. Remember, we're just plugging it into this equation right there. So it'd be the mass of this. Remember, think of this as just 2-point masses, an m there and a 3m there. So you got an m times r, that's his x value, plus 3m times the distance from here to here is 1, 2, 3r, divided by the sum of the masses. 3m and m is 4m. Okay, combine that together, that gives you 10mr over 4m, or 5/2 r. 5/2 r is 2.5 r's. There's the center of mass, that green spot right there. Now, if I wanted to find the I about this for the two pieces welded together, we'll first do it for the hoop right here. We'll use the parallel axes theorem. I about the hoop about this point. So we'll first, it's I about the center of the hoop, which is mr squared, plus the mass of the hoop times that distance squared, which is another mr squared, which just gives you 2mr squared. Now we can do for the I of the disk. I of the disk is I of the center of mass of the disk, which is 1/2 mr squared. Oh, except times 3m. So it's 3/2 mr squared because the mass is 3m. Plus the mass of this, which is 3m, times the distance from here to here squared, which is 3r quantity squared. So it gives you 3/2 mr squared plus 27 mr squared, which gives you 57 over 2, if I get a common denominator right there, mr squared. And now, if I wanted to find the I of the two put together, I can add them up. As long as they're about the same point, I can add them up. So it's just the 57/2 plus my 2mr squared, which is 61/2 mr squared. So from that piece of information and that piece, later on, we would be able to calculate how much time this thing takes to swing back and forth right here. Okay, so it just gives you some practice with moments of inertia right here.